Okay, so let's move on to part 2 of these algebraic integers or rings of integers, where we're actually going to prove that the algebraic integers form a ring. So before that, we're going to need some helpful theorem, and before that, I'm going to need some definitions. So I'm going to start with just defining something that we saw a little bit last time, but I just gave the definition of it as a set. So here's some basically some notation. So definition 2.1.13. Now let alpha be some complex number. And we let z alpha is going to be the ring that looks like as follows, whose elements are f look like this, where f is some polynomial in z of x. B, so this is the smallest ring containing z and alpha. So if you think of what the smallest ring would have, you'll see that all the elements have to look like, well, they're just some linear combination of powers of alpha. So I'm writing this as just, they look like some polynomials in alpha. This is just to give you an idea of what they look like. Notice that if we think of this instead of as a ring, but just as an additive group, we think of z alpha as an additive group. So forget that we can multiply things. Then it's generated by this set, 1 alpha squared, and so on. So every element in z alpha can be written as some linear combination of some alphas to some power as an additive group. So some sum of these things. So here's a definition of something being finitely generated. So definition 2.1.14. Again, alpha be some complex number. We say z alpha is finitely generated as an abelian group. If there exists a finite set, say B1 up to Bn, of elements Bi and Z alpha, such that every element of Z alpha can be written as this. It can look like some linear combination of my basis vectors, so some x1, b1, xn, bn, so some xn in z, xi in z. So if instead of having to use all of the powers of alpha, for example, we can only use, if it's enough to just use like the first 3 or the first n of them, then we say that this is finitely generated. So this is what it means for finitely generated. It's as an abelian group, as an additive abelian group. So here's the theorem that's going to be useful for proving that integers form a ring. So it's a bit technical, but it's quite useful, this result. 2.15 says the following. So let alpha be some complex number. Then the following are equivalent. What is it? So 1, alpha is an algebraic integer. 2, as an additive group, z alpha is finitely generated. 3, alpha is an element of some subring of the complex numbers, having the subring having being finitely generated as an additive group. subring of, which is subring of C, which is finitely generated. It's an additive group. And lastly, for alpha times A is contained in A with, this is A and C, some finitely generated reading group. Fin-gen additive subgroup. So here, A alpha just means the products of elements of A and alpha. So here, alpha A is a set of elements. Of the form alpha X for X and A. So if you take some finitely generated additive subgroup of C and you multiply it by alpha, then if it stays inside of A, if you take all the elements and multiply it by alpha and it stays inside of A, and this is also equivalent to all of these things. So let's begin to prove this. So let's go 1 implies 2. Since alpha is, so we're assuming that alpha is an algebraic integer. It is an algebraic integer. It's the root of some monic polynomial, so m alpha. Let's say m alpha has integer coefficients and or is monic. Let the degree of m alpha, let's say that this has degree n. We claim that I want to find, so I'm trying to do 1 implies 2. I'm going to claim that I know what a basis for z alpha is. That way, if I have a finite basis and this is finitely generated, my claim is that 1 alpha to the n minus 1 is a basis, or I'd say, yeah. Which would prove that it generates as an additive group. So everything can be written in terms of these powers of alpha. To do this, so note that if I have f of alpha and z of alpha for some element of z alpha, I wrote them up here as looking like, where was it? I wrote them like looking at polynomials which I've evaluated at alpha. So if I take some element in here, then as usual we do polynomial long division by poly long division. We have f of x equals q of x m alpha of x plus r of x with the degree of r strictly less than n, which is the degree of my minimal polynomial. If we evaluate alpha, we get f of alpha is the same thing as r of alpha. So if I have any element in like this, which somehow had bigger powers of alpha to the n showing up, then actually f of alpha equals r of alpha, so I can rewrite it as something of smaller degree. We get this. So since the degree of r is strictly less than n, we see that r of alpha is in the span of 1 alpha to the n minus 1. So yeah, if I had some, say, alpha to the n plus 1, I divide this by m alpha and I get a remainder, and this remainder is now some polynomial of degree less than n. So it looks like some element of smaller powers of alpha showing up. And this proves the claim. It obviously, so as we saw before, I've checked that it spans linearly independent, is somehow clearable, because we did this in a proof before. If you assumed, for example, that this weren't linearly independent, then there'd be a dependence relation between them. That dependence relation would now give you a polynomial of degree n minus 1, which alpha satisfies, but alpha, we said the minimal polynomial has degree n. So this has to be, as soon as I check that it spans, I've checked that it's I also know that's linearly independent, so this is actually a basis. Okay, so now 2 implies 3 implies 4. I claim this is trivial. So let's have a look at what it says. So alpha, this is finitely generated. Alpha is some element of some finitely generated group. So if this is finitely generated, then alpha clearly is some element of some subring, because just take z alpha in here. And now again here, take your A to be z alpha. Then, well, okay, so here there is some subgroup which is finitely generated. So if you take that subgroup which is finitely generated, if you multiply all the elements by alpha, it's going to have to stay inside of it. So 2 implies 3 implies 4 is, it's true, there's nothing to check. So we're going to check so we need to check that 4 implies 1. So what does 4 say? It says that I can find some subroom, some finitely generated subgroup of complex numbers, such that when I multiply it by alpha, it stays inside itself. So alpha time, if I take all of its elements and multiply them by alpha, the result stays inside of my subgroup. So I'm saying it, assuming it's finitely generated, so let A1 to AR be a basis of A. Then as each, by assumptions, when I multiply each of these basis elements by alpha, I stay in A. We can write this again in terms of a basis, in terms of this basis. This we can again write this. I can write this element in terms of this basis, right? So each of these is some element in A, and this is a basis for A. So each of these things can be written in terms of a basis. So I end up with like some system of equations. So like A alpha 1, I do this, and I get like x1 1 A1 plus x1 r AR, and I do A alpha 2. It's gonna be A21 A1 A2R AR alpha AR equals XR1 A1 ARR XR. So I take each of these basis elements and multiply them by A, and I rewrite it in terms of my basis. So I end up with some system of equations like this, where the Xij are elements in Z, because I'm talking about finitely generated. Remember, for finite generated, I assumed that it was like over some additively finite generated. So if we put this in matrix form, this means the system of linear equations form we have. Matrix form, if we let X denote this matrix of Xij's, and A be this vector of A1 to AR. So in matrix form, we have X times A transpose equals alpha times A transpose. This is what my turning this is this side, this is this side. This is what me turning it into a matrix equation is. Here just denote. Here T denotes transpose, as usual. Therefore, if you think about this alpha is some eigenvalue of this matrix X. This is what this is saying. Therefore, alpha is an eigenvalue of the matrix X, which if you come back here, you'll see that this has integer entries, and the first lemma that we saw in the last lecture, was that if we had a matrix with integer entries, then its eigenvalues are algebraic integers. So this is the alpha is an eigenvalue of a matrix with integer entries, therefore it's an algebraic integer, which has integer entries. So I give it this, so by lemma 2.1.2, alpha is an algebraic integer. Done. Great. So this is a technical theorem, but it's actually will be quite useful. It's the key to proving that these things form a ring. I think I've said that a million times already. Maybe I should stop. So, okay, let's see how to. Here's the corollary. So here's the corollary that we want. 2.1.16. So if I let alpha and beta be algebraic integers, then alpha plus beta and alpha beta are also algebraic integers. So if you stop to think about how you would do this, if I hadn't, before we see the proof, you'd have had to look at alpha and beta. You know that each of them satisfies some monic polynomial with integer coefficients. Then you'd have to try and find some other monic polynomial with integer coefficients which alpha plus beta satisfies, or alpha beta satisfies. Then it's not clear how to take the minimal polynomials for each one of them individually and combine them. So like if you can't add if you add the minimal polynomials, the roots of that won't be alpha plus beta. If you multiply them together, the roots of that won't be alpha times beta. So it's not clear how you would do this if you're trying to do this by hand. But it is true that we can prove that there has to exist one. So here's the proof of this corollary. Since alpha and beta are algebraic integers, by the previous theorem, so theorem 2.1.15, we have that Z alpha, the second bit of this theorem, where that Z alpha and Z beta are finitely generated, so gen finitely generated as additive groups. Moreover, the ring, so if I do Z alpha beta, so think of this as the smallest ring containing alpha and beta, is also finitely generated. It's also finitely generated because since if I have A1 to AN, a basis for Z alpha, and B1 to BM, a basis for Z alpha, Z beta, then if I do AI BJs over I and J, this is a basis for Z alpha beta. This is the smallest ring which contains both of these rings. Take any element in here. Everything that has an alpha in it, write it in terms of the basis for Z alpha. Everything has a beta in it, write it in terms of the basis for Z beta. So it's all the elements themselves are all going to be formed by this, be written in terms of this basis here. So this Z alpha beta is also finally generated. Now, alpha plus beta and alpha beta are elements of this ring, are in as alpha beta. Then if you go back to this theorem and look at the part 3, then by 2.1.15, I say part 3, we know that they must also be they must be algebraic integers. Cool. So although I've not found what the minimal polynomials of these two things are, and in general that's really tough, we know that there exists some polynomial because this ring is finitely generated. Therefore, its elements have to be algebraic integers. Just go back and have a look. So if you look at part 3, that says if I take any element of sub ring which is finitely generated, then 3 implies 4, which implies 1. So alpha has to be an algebraic integer. So here is a ring which is finitely generated. Here are some elements which are in it. So both of these elements have to be algebraic integers. So here's another corollary of this. So corollary 2.1.18. If K is a number field, then OK is a ring. Proof, well, this basically follows that one from the above. Since alpha and beta are in K, okay, so not since, so take alpha and beta in K, algebraic integers, then we know that alpha plus beta and alpha beta are also elements of K because K is a field. Therefore, alpha plus beta, alpha beta are also algebraic integers in K, so they are in OK. Right. So I've taken two algebraic integers. Oh, let me just, I should start using my notation now. So alpha and beta in OK. Then I know that the sum of two algebraic integers is an algebraic integer, and the product of them is an algebraic integer. All I need to check is that I've stayed inside K, that I've not left K for some reason. But because alpha plus beta is in K and alpha beta is in K, then this sum has to be inside of K. So now we know that OK is actually a ring. It's called the ring of integers. This is going to be these rings of integers are going to be the ones that we study a lot. So I'll look at their ideals, and we're going to look at how many of their ideals are prime ideals, principal, and not how far they are from being principal. This is where these class groups come in, and so on. And we'll use this to solve like Diophantine equations later and whatnot. But for now, let me just give you some more results on algebraic integers and how to spot them. So here's a proposition 2.1.19. If K is a number field and alpha is some algebraic integer, then the trace from K to Q of alpha and the norm from K to Q of alpha are in Z. So the trace of and norm of an algebraic integer is an algebraic integer. This isn't hard to prove. We could have done this before. By corollary 2.1.9, we know the field polynomial has integer coefficients, and therefore by proposition 1.7.3 we get the result. this was the proposition that told us that we could figure out the trace and the norm by looking at the characteristic polynomial, this field polynomial, that the trace was the second coefficient in the characteristic polynomial, and the determinant and the norm, which was the last coefficient in there. And now I've told you that this polynomial has integer entries, so the trace and norm have to have integer entries. Let me give you a warning here. So warning, the converse isn't true. It's not true. For example, you can take, have fun with this, but you can check the following. Square root of 1 plus root 17 over 2. This has integer trace and a norm, but is not an algebraic integer. Great. Also, okay, yeah. So, yeah, this helps us to tell if something isn't an algebraic integer, because if you find the norm and its trace aren't integers, then the number that you started with couldn't have been an algebraic integer. It's useful for these sorts of things. Now, you might ask yourself, what does this ring of integers look like? You maybe be tempted to think, well, it maybe just looks like some z alpha. Maybe this is what the rings of integers always look like. It's not always the case. The rings of integers can be slightly larger, but they're always at least this big. So what's my next proposition? So let alpha be an algebraic integer, and I'm going to let k be q alpha. Then z alpha is contained inside OK. So it could be the same whole thing, but it might not be. Proof. Since by definition alpha is in OK, it's an algebraic integer and it's clearly contained in k, because k is my field. Since by definition alpha is OK, then we know that z and alpha are in OK, right? So this is a ring. It contains, every ring contains the integer. So every commutative ring of characteristic this is f characteristic 0. This contains the integers and it contains alpha. So it has to contain the smallest ring, which contains z and alpha. So it has to contain z alpha. We know that z and alpha are in OK. So z alpha is in OK by definition. So the definition that we gave was 2.1.13, which was just that this is the smallest ring which contains these things. Great. So the ring of integers always contains this thing, z alpha. So if I asked you what the ring of integers was for some field that looked like this, then it might not always be z alpha, but at least it contains it. And it's not a lot of the time it's not the same thing. Sometimes, a lot of times it's bigger. Even in the case of that we saw last lecture, where, let me just scroll back. I think I've gone too far. Yeah, for algebraic integers in quadratic fields. So if you look at square root d, it's not always q square root d. Sometimes it's something slightly larger. It's q1 plus root d over 2. So you're somehow, it's not OK, can be this ring, but sometimes it can be something bigger. Now let me give you another warning, which is that, warning, if I have k equals q alpha is a number field, then it's not always the case that z alpha equals OK. I've just told you that. C theorem 2.1.11, for example. But you might ask if it's always possible to find some, say, alpha primed such that OK is Z alpha prime. So you say, well, maybe it's not this alpha that I have found here, but maybe there's some other element alpha in K for which this is true. Again, this is not always true. You might ask if this is always possible to find some alpha true. This is not always possible. There's an example of this in one of the problem sheets. This is not always possible. In other words, these rings of integers aren't always generated by a single element. You can have rings of integers which generally need 2 or more elements to be generated by. It's not always possible. For example, I'll give you an example, but this would be hard to check. For example, if alpha is a root of, what was it? You have to x cubed plus. So I think for quadratic fields, it is always true that you could find one thing, like we saw it in theorem 2.11. You can always find one thing which generates it, but once you go up to cubics, then this stops working. If you had alpha to be a root of this, and k was q alpha, then OK is different from Z, say beta, for all beta in O, for all beta in K, say. So you're genuinely going to have to need, for this ring, you're genuinely going to have to use like an alpha and a beta. You're going to have to use 2 different elements to do it. So this is talk about monogeneric, generated by one thing. So the slogan is rings of integers aren't always monogeneric. But why do we care about the ring of integers instead of just Z alpha? What's better about having this ring? Like, I know what Z alpha looks like. I don't know what OK looks like. These things might be a bit weird. But here's a good reason. You'll see why this is a useful thing later on. But here's one good reason why the rings of integers are actually better. So proposition 2.1.24. So the following, let K be a number field. And R a subring of OK. My O's are getting even more curly. Some subring of OK, which generates K as a field, i.e., the field of fractions of, frac. By frac I mean the field of fractions. Frac R equals K. So if I have some subring whose field of fractions is again K. So let's assume that we're in this situation. Then if R has unique factorization, then R equals OK. So the only unique factorization ring that you can have is going to have to be the ring of integers. You wouldn't be able to have a UFD, unique factorization domain, if you weren't already, if your ring wasn't the whole thing already. And so let's prove this. This will be quite useful for checking later on if a ring of integers if something that looks like Z adjoint alpha is a whole ring of integers or not. So proof. So we know that R is, by definition, we know that R is contained in OK. So we want the reverse inclusion. We want to check OK is contained in R under these conditions. So let alpha be some element of OK. Since we have assumptions frac r equals to k, we can find some delta and gamma and r such that alpha is gamma over delta. This is what, alpha is some element of k, frac r is k, so field of fractions of r, which means these are just a set of elements that look like quotients, so like two elements of r. Every element of k can then be written as in this form. And if I do this in lowest common form, so I can make that I can assume that with delta and gamma sharing no common factors other than a unit. So I can just assume that it's a fraction in lowest terms. Now, since alpha is an algebraic integer, it has some monic polynomial, so we can find, it satisfies some monic polynomial. We can find a monic polynomial such that, we have, I'm saying polynomial, but I can find an expression of this form. Plus a0 equals to 0, so I have to satisfy something like this, ai's and z. So now take this expression and plug it in, and then multiply clear the denominators. So if you multiply through by delta to the n, we get the following. We get gamma to the n plus an minus 1 gamma to the n minus 1 plus a0 equals to 0. Just replace alphas for gamma over delta. So you have a bunch of over deltas, and now just multiply through by a big enough power of delta. Oh, I made a typo here. So this should be, here you should have one power of delta, and here you have a0 delta to the n equal to 0. Right? So now, since we're assuming that R has, now we're going to have to come in with the assumption R has unique factorization. So since R is assumed to have unique factorization, we see that if this is pi is an irreducible factor, this is var pi, it's a variant of pi. It's like, I think it has, I can't remember what the actual name is, but it's a pi with a line on the top. That's like a curly pi. So if this is an irreducible factor of delta, then I think this may be called pomega, that might be the word. Then I'm just going to call it var pi, because it's a latex term, or just pi. Then var pi is an irreducible factor of gamma to the n, and thus, so if you look at if I take any irreducible factor pi of delta, it's going to show up in all of these. So if it shows up in all of these things, it's going to have to show up in gamma to the n, and therefore have to show up in gamma. Again, because we're assuming we have unique factorization. To be a factor of gamma to the n, and thus of gamma. But we assumed that this was in lowest of possible terms, that delta and gamma, I'll just take r co-prime, because they had no common factors other than units. So delta has no irreducible factors. Other than units, right? So if I had a irreducible factor of delta, it would also have to reduce a factor of gamma, but we assume that we had taken this to be in lowest terms. Obviously, we can just cancel them out from here. So delta just has to be a product of units, so delta is a unit. So alpha, which was gamma over delta, this is just, well, let's just say this is just gamma, which was an element of R. So R contained. So OK is contained inside of R, right? I took my element, so let's highlight what I did. We knew that R was contained in OK by assumptions. So we need to do this with the reverse inclusion. So I take an element of OK, and I want to prove that it has to be inside of R. This is what this line proves. What do I do? Well, I use the fact that I've assumed that my ring R, its fraction field is K. Therefore, I write alpha as gamma over delta, which I assume are co-prime. Now, I used to use the minimal polynomial for alpha to have some integral relation like this. I just multiply it through, and I end up with an integral relation like this. And now, if you think of what the irreducible factors of delta can be, if I had any irreducible factor of delta, because I have this equation, we'd also have to divide gamma to the n, but I would also have to divide gamma. This contradicts this thing being reducible, so there can't be any reducible factors of delta. So this delta is just a unit. So alpha just looks like gamma in R. Alpha is an element of R. And this gives a result. And so we're done. So we're going to move on towards trying to find. So I've told you that, well, these rings of integers, they might not look like Z alpha or Z beta, but let's try and find a basis for them so that we can at least know what to write every element as in. So this is what we're going to do in the next lecture, but let me just give a definition before we end. So here's a definition to finish things off. Definition 2.1.25. So let K be a number field, and let B1 to Bn be a basis for K over Q, so as vector spaces. So what we're going to do is we call this an integral basis if the ring of integers, if OK is the same thing as Z B1, comma Bn, which I'll remind you this just looks like a set of elements that look like x1 b1 xn bn such that the xi's are in Z. So as a set, that's what it looks like. So I call it an integral basis. So I'll say I have a basis, but if I'm lucky and my basis is what I call an integral basis, then it will, if I just look at it over Z, this span over Z, then it's going to generate to me my ring of integers. And what we're going to look for later on, what we're going to talk about is how to find an integral basis, so that we can know what the rings of integers are. Because once I know a basis, then I can write everything in terms of that basis, and I really understand this ring. So we'll look next time. We will begin. Well, start to look for ways to find such bases. Okay, and that'll do it for